Okay, everybody, this is going to be a quick video. We're going to talk about paired t-tests. Okay, and this is what our book is calling and our homework's calling 10.4. Okay, a paired t-test. So what we have been used to doing, in 10.1 and 10.3 is we've been finding, we've been dealing with differences in means of two groups or proportions of two groups. So maybe we were comparing, the average height of all men to the average height of all women. Okay, and so, maybe our null was that there's no difference in the average height. The difference is 0. And the alternative was maybe that, the average height of men was greater than women. So if I were to subtract these, I'd get a positive value, something like that. We were comparing the averages of two different groups, okay, whether it be a hypothesis test or a confidence interval. That's not what's going on here, okay, so this is not what's going on in this problem. Okay, so we are not estimating two separate population means. We're not doing this here. Okay, instead what we are doing is we are estimating or testing the difference between pairs of data. Okay, so we're going to take two sets of data, but we're only going to look at one set of differences. We're only going to do analysis on one set of data. All right, and so here's just, again, a difference between the two, and I think it's going to make sense when we look down at this example here. But when we're dealing with two sample stuff, so again, this was like 10.1 and 10.3, okay, for two sample stuff, we are measuring the difference between two means or proportions, right, depending on what the problem is asking for. When we're dealing with paired information, we are basically taking a single mean of the differences between the two data sets. And so this could be used to determine if there's a difference in some sort of experiment, like before or after some treatment. Or maybe there's a difference in twins, okay? Or there's a difference between left and right, or husband and wife. Basically, data values that make sense to pair together, okay? So let's take a look at this problem and see why it makes sense that we would use a paired test here. So listed below are systolic blood pressure measurements taken from the right and left arms of the same woman. Use a 1% significance level to test for a difference between the measurements of the two arms. Okay, so what we have here are these numbers represent different women. And so maybe we have person A, person B, person C, person D, and person E, right? And so this represents the blood pressure taken from the left arm of person A versus the right arm of person A. And this represents the blood pressure taken from the left arm of person B versus the right arm of person B, and so on. So we're only looking at 5 people here, right? A, B, C, D, E. Those are my 5 people, women that we're looking at. So can you see why it makes sense in this case to pair the data? It wouldn't make sense to compare the left arm with person A to the right arm of person E. That wouldn't make sense because they're different people. So inherently there's difference in their blood pressure, right? In other words, it may not have anything to do with left and right arm at that point. It may have to do with other health conditions. Okay, so if you really want to see if there's a difference between blood pressure in your left arm among your right arm, you don't want to do that, like take all men's left arms and compare it to all men's right arm blood pressure measurements, because then you're basically kind of you're sort of comparing oranges and apples, because some of these men here, well, kind of like what I mentioned here, there's different health considerations to take into account, and so it wouldn't make sense to take the average of every adult male's left arm blood pressure and compare it to their right, because again, we are mixing people that shouldn't be mixed. Okay, what would make more sense is to say, all right, let's just look at person A. I mean, they have the same blood pressure in their body, so if you really want to see if there's a difference between left and right arm, let's compare their left and right arms separately. And let's do the same for person B. Let's compare their left and right arm measurements, and the same for C. And this is going to allow us to see if there's really a difference between left and right arm blood pressure measurements and sort of negate the idea that you might be comparing people with different underlying health conditions. So what we do here is we do not take the average of all the left arms. We don't find the average of the left arm measurements and the average of the right arm measurements and compare them. We do not do that. Okay. Again, because then I'm comparing, then I'm making a comparison with person A, B, and C here to person D, E, and C down here. We don't want to compare them together. Instead, what we do in this paired data test is we're looking at the differences for each of these values. So really what's going on in a paired test is you're looking at each individual person, right? And you're seeing what's the difference between those two measurements. So I'm just going to take left arm minus right arm. Left minus right. Doesn't really matter the order you do it. But if I take the left arm measurement minus the right arm measurement, this I get 13. Here left arm minus right arm measurement would be -2. Left arm minus right arm, let's see, that would be 18 if I'm adding it right. Left minus right would be -1, and left minus right would be 21. So really what I'm doing is these are the data values I'm interested in. I want to see if those data values suggest that there's a difference between left and right blood measurements. I mean, some are or blood pressure measurements. Some are high, some are low. So the question is really, we want to analyze this set of data. And I'm basically looking at what's the average of the differences. Let's say we want to analyze this set of data. We are interested in the average of the differences. In the average difference, sorry. Let's call it mu sub d for difference. And so if the average of the differences is 0, let's just say that hypothetically the average of all the differences is 0. Well, what that means is that there is no difference between your left and right arm measurements. And I mean, here we see some differences, but maybe this was just luck of the draw and this was the 5 people we chose. This is a very small sample size, so maybe if I did some more, I would get some other negative values to help balance this out. Okay. So let's try and do this problem here. It says use a 1% level of significance to test for a difference in the measurements of the two arms. So if I were to do a hypothesis test here, my null hypothesis would be that the average difference in blood pressure between the two arms, the null would be that it's 0. Remember, null always has to use an equal sign. And so it would be that there is no difference in the averages. And the alternative to that would be that there is some sort of difference. Now, they don't give us any indication of, which one would be larger or not. So I think our alternative would just be that there is some sort of difference, that the average difference between these blood pressures is not 0, that it's something other than 0. There is a difference between them. And they told me to use alpha to be 0.01. Okay. 2, name the procedure. This is a paired t-test. And I'll show you how to do it on StatCrunch. 3, just to save our sanity, let's just pretend and assume that all the conditions were satisfied. Even though here we don't have a large enough sample size, I want to get down to the results. So let's just assume it's been met. Okay, it definitely hasn't because of the sample size. Sample size is too small, say that. Remember, I'm talking about averages, so I need at least 30 data values here, which we don't have. All right, let's talk about doing the test. So again, it can get confusing because you're thinking, all right, well, I'm looking at two groups of people. But actually, the test you're doing is just a one sample test, right? You're only testing a mean, right? So this is really just a one sample t-test. And that's exactly what we did back in chapter 9, right? So there's really nothing new here as far as the test is concerned. You already know how to do a one sample t-test. You would find the test statistic, right? Which means you would first need to find the sample mean and sample standard deviation out of this data set. And then you would find the p-value and interpret your results. I'm just going to go ahead and do it all on StatCrunch and show you how it does it. But again, I hope this idea is making sense that what we're analyzing is a single set of data, the differences between these two data values. And in a case like this, it makes sense to pair the data, right? Okay, because again, I want to compare the results of woman A to woman A, right? Not A to some other person, B or C. Because again, then there's underlying conditions that can affect the blood pressure, not just the fact of whether it's on their left or right arm. So when you're just trying to compare the difference of this paired data, you're doing a one sample t-test, all right? T because it's one sample because I'm dealing with a mean, right? And then t-test because I don't know the population standard deviation here. I'm going to have to rely on my sample standard deviation. Let's take a look at what StatCrunch does for us. So I already loaded the data into StatCrunch here. So here I've got the left arm blood pressure measurements and the right arm blood pressure measurements. And then I also wrote down the differences because I just want to show you two ways you could do this. So one thing you could do is you could go to Stat. Let's try again. Stat. T-stats. Now here we see the option we want to choose paired data. So T-stats paired data. It's going to ask where's your sample 1 coming from, and so I'm going to say that's the left arm column. Where's your other sample data coming from? That's the right arm column. What's important is to make sure these line up. So this is person A, this is person B, this is person C, D, and E. In other words, don't mix them, okay? Make sure that each row contains one person's information. All I need to do is make sure my null is correct. The average of the differences is 0, and the alternative is that it's not 0. Let's go for it. So here's what we got. There's the test statistic you would find, and there's your p-value. All right. Now, just to prove that all we're doing is a one sample t-test on the differences, I also wrote down a column with the differences. So here was the difference between each of these, right? This is what I wrote on OneNote. Woman A, there was a 13 point difference between the left and right arm. Okay, I took left minus right. So let's do a t-test on this data and see that we get the exact same thing. If I go to t-test, t-stats, but I'm only doing one sample here with data, right? I'm doing a one sample t-test on this stuff right here, on this data. So I want to use it from this column, the differences. The null is that the average is 0. The alternative is that the average is non-zero. Whoops. If you see, I get the exact same results. If I can get it to settle down here. There. Right? Same p-values, same t-stats, same exact results. This is what the computer is doing when you tell it to do a paired t-hypothesis test. It says, okay, well, I'm going to subtract these and get their differences, and then I'm going to do a one sample t-test on those differences. So it's using just chapter 9 techniques. All right. Again, it can be confusing, especially in the midst of all these chapter 10 problems where you're comparing averages of two groups, like the or percentages of two groups, you know, percentage of men versus percentage of women that want to have kids or something like that. But for certain things that you're trying to study, it makes sense to pair the data together. All right, and so this is a perfect example where we're looking at the difference in blood pressure between left arm and right arm. It makes total sense that you would compare the results for each individual person and don't mix up the people, because like I said, then there's underlying conditions that can cause these numbers to be different. So p-value, so t-stat is 2.05 and 0.11. Okay, so let's just write that down, finish the problem. So I had a test statistic, so this is brought to us by StatCrunch. We had a t-stat of 2.05, right? And then my p-value was 0.11, okay? And so since my p-value was fairly high, it was definitely higher than what our level of tolerance was, this means that we fail to reject the null, right? This was, in other words, the probability of getting the results we got, there was only 11% chance that we should have gotten the data we got if the null was true. Well, that's kind of low, but it's not what we consider too low. Remember, below alpha is what we would say, okay, that's too low. You've gone too far. I reject the null. In this case, we're low, but we're not too low, so we do not reject the null, okay? Since alpha is greater than, oops, sorry, since our p-value, darn it. Then alpha, we fail to reject the null. And so what that means is that the data does not suggest that there is a difference in the averages of left and right blood pressures measurements. Even though we see some differences, it's not a big enough difference to suggest that there's going to be one among all the data. And so let me add that. The data does not suggest a difference in blood pressure values or measurements between left and right arms. Blood pressure between left and right arm measurements. Again, we shouldn't take that to the bank in this one because our data, we had way too small of a sample size, right? So this was not a really good test as far as feeling confident in our results go, but the idea was just to lay out how the heck you do a paired test or what a paired test is. Okay, so I hope that makes some sense. Again, that can kind of be a challenge in Chapter 10, is deciding when you should pair the data and when you shouldn't. A lot of the problems you encounter in the homework, they tell you, they say the data has not been paired or should not be paired. Other times it's up to you. And so I think you just kind of need to keep your eyes open when doing the analysis and think of, does it make sense that that I shouldn't put everyone in a big group together, or does it make more sense that I would look at the different results from individual pairings of people? Like maybe you're comparing IQ score of twins, right? And so you would want to look at, if you're going to look at the IQ difference between two twins, you would want to look at, twins number one, right? What was their score minus their brother's score? And then the second pair of twins. What was their score minus their sister's score or whatever. It wouldn't make sense to compare this twin to some other twin that they have no relationship to, right? That's not basically showing a difference in IQ between twins, or it's not allowing us to analyze that. So sometimes the data just makes sense to be paired. I think you just got to keep your eyes peeled for when that seems appropriate. All right, I hope this made sense. I will see you all later.